Good morning. My name is Bruce Pint, and I'll be talking about environmental resistance and how it affects superalloys and maybe some strategies of how to assess it. I'm from the corrosion group at Oak Ridge, and I'll be talking about a lot of research that's been sponsored by the Department of Energy. I've given similar talks in the past, and I think I've been a little annoying to this type of audience. I'm okay with that. Started back in 2004, where I talked about the problems with oxidation resistance of high temperature materials. And it was interesting that year that a poster about a material called noburnium won the best paper award. It never really got off the paper, I don't think, because you can Google it and see how far it's developed. There was a paper that came out from that talk with my colleagues, Jim DeStefano and Ian Wright at Oak Ridge. Made a presentation at TMS in 2009, 2014. That was work dedicated to Jim DeStefano, who had passed away the previous year. And then the folks at Material Science and Technology asked me to write a little assessment based on that presentation. So you can see that paper as well, some of the thoughts I had about it. If I go back to the summary in 2004, I have to say that not much has changed. As we go to higher temperatures, oxidation issues become more important and harder to ignore. I think it's a foolish strategy to think that practical high temperature materials for normal applications are going to be developed without inherent oxidation resistance, and I should say, and adopted. And then, again, 2004, quite a while ago, talking about combustion environments and aluminum forming substrate, that aluminum forming alloys are going to have a strong advantage because aluminum is more stable than some of the other thermally grown oxides. And I talked a fair amount about state-of-the-art nickel-based superalloys. And I realized that might sound dated, and the kids today might call me an old man. I'm actually not a baby boomer, but I have been doing this for a long time. And the last point, coating should not be considered prime reliant. So 2014 comes around, and I made some comments then. When I was in graduate school, everybody who was at this PhD defense remembers John Elliott said to the candidate afterwards that what he had presented would only impress the uninformed. And so that's not many people make that kind of harsh comment today, but I do believe that, life's short, research dollars are scarce, and we should all be pushing to, get to the bottom of things. If you're worried about ductility, then measure it. If you're worried about embrittlement, or you have a coating that's going to prevent embrittlement, then prove it. Don't just talk about it or show nano indentation. Show some properties. And I do believe there's a gap between research and application. And, that goes back to this issue of who are you trying to impress? You're trying to get a paper written, or are you trying to impact the technology that you're working on? You need to tie that development to reality, become educated in the key issues, and talk to people in industry. And if you can impress them, you probably got something. And just repeating from 10 years earlier, we shouldn't think of coatings as being prime reliant. Certainly not for power generation applications that are of interest to the Department of Energy. So talk about environmental resistance. Let's start by posing a few questions. What applications require high temperature materials? Things like aero engines, power generation, chemical processing, furnaces, and what kind of service times do these applications require? And of course, longer is always better, But if you're talking about an aero engine, you better be on the wing for at least 5,000, if not 15,000 hours. You might get away with shorter times for military engines. They're willing to pay more for performance, but that's a pretty narrow scope. Maybe even shorter times if we're talking about things like missiles. And when we start talking about power generation, though, reliability is really the key. So you better be talking about 40,000 hour lifetimes. If you're talking about a 30-year plant life, it's 250,000 hours. Nuclear folks talk about 60-year plant lives. The fusion people, they'll settle for a fraction of that. But it's something to remember when you're designing your experiments. A comment I've gotten in the past when I've made presentations like this, oh, we couldn't do that during a PhD thesis. Well, you know what? 1,000 hours is still only 6 weeks. And if you devote only a fraction of your experimental work to oxidation testing, you can do a fair amount if you want to. And again, who are you trying to impress with your 10-hour test? Is it relevant? So maybe another question I'll just throw out there. Do you know where your electricity comes from? Do you know what's happening on the grid and where things are going? And maybe another thing is, even if you do know where things are, did you know that we've had a flat environment for the last 10 years? Remarkable, after a sort of 100-year where we're just increasing all the time, constantly building new generation. We've had more than 10 years now since the 2007 peak, I guess 14 years, that there really hasn't been any increase in demand. And so something has to come off the grid for new generation to go onto the grid. And so as renewables have jumped up, coal has really taken a beating, but natural gas has come in to replace it. So we're still using a lot of fossil fuels. But if you think about it, we're on this trajectory of using more natural gas. But if we want fossil fuels to go away, utilities are reluctant to purchase turbines because that could be a stranded asset in the future. And then think about what service temperatures are required. And I know people like to talk about really high temperatures for things like turbines, but again, maybe that's not really the future anymore. And certainly higher temperature is going to give you higher efficiency. I have a plot here from Bridge Seth at Westinghouse showing the turbine inlet temperature and how turbine efficiency is going up. But if you looked at this is the ASME allowable stresses for a number of structural materials, their properties are declining rapidly in this sort of 600 to 800 degrees C range. And, again, and this is why when you look at a coal plant, they're only at 607 degrees C, and they call that ultra supercritical, USC. Nuclear plants, man, they think 300 degrees C is hot. But, I know coal plants, I'm an old guy. Maybe most of those will be shut down by the end of the decade. So what has interest right now is that ARPA-E is about to kick off their ultimate program, and they want to look at materials for 1300 degrees C. They have metrics to achieve or creep and fatigue at 1300 degrees C, but the metrics don't specify the environment. So I am part of this program, but just for the mechanical properties testing and not so much for environmental effects. And they are going to focus on refractory metals, as you can glean from their logo. And so the point I want to make about how we assess things is that we can very easily replace our coupons with tensile specimens if we want to. I recently got a quote, and I was paying about $20, a little over $20 each to have coupons machined from some cast materials that I needed to evaluate. And typically these tensile specimens, depending on the machine shop and what kind of how busy they are. We're paying $50 to $75 a piece for these tensile specimens. So relatively modest increase in the cost of the specimen. And honestly, if you can test a coupon, you can test a tensile specimen. And if you can coat a coupon, you can probably coat a tensile specimen. Again, if you want to, if you really want to know what those properties are. And we've made different versions of this, increasing the gauge, the depth, thickness. So we get a 2x2 gauge for doing creep testing on some of these. And, you can look through the literature and find examples where we've reported things like that in the past. I'll just give you a couple examples real quick. Again, this notion about you can do everything you want with a tensile specimen that you can do with a coupon. So here's a study where we're looking at turbochargers. Again, might think this is a little bit outdated, but again, there is interest in high efficiency combustion engines while we wait for electric vehicles to take over. And again, with these tensile specimens, we can measure mass change. We can report kinetics. We can section them, look at the reaction products. Again, these are all from SS3, sort of 25 millimeter long specimens, and then we can break them. And the interesting thing about this study was that we were expecting to see that the titanium aluminides were going to embrittle during these exposures at 850 and 950 degrees C for 1,000 hours at 850, 500 hours at 950. And in fact, they didn't lose any ductility. So surprised, and apparently those materials have come a long way. Certainly, they had thicker reaction products, but we didn't see the embrittlement that others had reported. And another test where we did see some results is this experiment for the fusion energy, where we had a chain of specimens in flowing lead lithium, and you can see the temperature range that these are exposed at. And when we break them afterwards at room temperature, you can see that we've had a strong increase in the yield strength and an associated decrease in the ductility. And this is a typical 475 degrees C embrittlement, but able to measure that using these type of tensile specimens. But the one thing we did able to prove in this study was that if we annealed the specimens at the same temperature, we get the same effect, in the same temperature range, I should say. We only selected 3 temperatures to evaluate and got the same type of embrittlement going on. So again, it wasn't the lead lithium environment per se that we were doing the environmental test. They alloys performed very well at that temperature, but again, can use our SS3 specimen and do some nice TEM work. There's some results from King and Unisec, and Steve Paul were the primary authors on this publication. And you can see that we did form the alpha prime, very fine scale. You can look at this 70 nanometer micron mar, and you can see that alpha prime formation for the chromium enrichment, and that's why you get the embrittlement. Really nice microscopes nowadays can see things like that. And finally, when we did our next experiment at a higher temperature, we didn't see any of this effect. As we went to higher temperature, we got away from that embrittlement range, and now we didn't see any instance of really strong loss in ductility or change in the yield or ultimate tensile strength. The shaded areas in each of these plots is the starting properties of the APMT material. And this was reported a little more recently, again, in the Journal of Nuclear Materials. And again, chain of specimens so that we have different temperature exposures for each of the specimens in these 2 experiments. Now, let's get back to refractory metals. I don't have as many results, frankly, with refractory metals. Haven't worked in that space in a long time, but there are some unusual things, and perhaps you know this, that the majority of refractory metals have a high solubility for oxygen, and they do form stable oxides, but they tend to grow really fast. Here's an example, the specimen mass gain at different temperatures. NB1ZR compared to moly get very thick oxides forming on the NB1ZR. This is actually an experiment to simulate the Mars environment. The opposite is moly and tungsten, where you have low solubility for oxygen, but relatively unstable oxide. So you have a tendency at high temperature for the oxide to evaporate. And, so the question becomes, which problem do you want to address? And so, again, my mentor, Jim DeStefano, got a good laugh out of the fact that when he started in the 1950s, GE was working on moly-based alloys and Pratt & Whitney was working on niobium alloys. And when things reshuffled in the 1990s, they had reversed. And he felt that Pratt & Whitney had learned a few things and chose a different pathway when they had an opportunity. So one more experiment that Jim and I did. I listened to him for many years talk about what he did on his PhD thesis on NB1ZR. And so I decided to repeat that experiment for some vanadium alloys that we were studying for the fusion program. And we're looking at how vanadium alloys would react in a helium environment, perhaps with some oxygen impurities. And so the interesting thing is, if you expose a vanadium alloy at say 600 degrees C into a low partial pressure of oxygen, you have oxygen uptake. The specimen comes out shiny. Here's an example down here. But if you pick up enough oxygen, you'll eventually embrittle the alloy. So here's the elongation. You start off at about total elongation over 30%, and pretty soon you're down to less than 5%. And then at the same time, as you're picking up oxygen in the alloy, the yield and ultimate strength are increasing. And so it's not particularly surprising. When you do the same experiment in a high partial pressure of oxygen, or in this case, we did it just in 1 atmosphere of helium, you can grow an oxide on the surface. And so picture of it right here, there's an oxide on the surface, and you can calculate that that's the equivalent of picking up about 5,800 parts per million of oxygen. And that's way off the scale of this plot here, but we still had 10% total elongation, because most of the oxygen was actually on the surface. But here's the problem with high oxygen solubility. That oxide is not thermodynamically stable. So again, we just repeated what Jim had done about 50 years earlier, or maybe 40, that 2,000 hour anneal at 700 degrees C, the specimen comes out and there's no longer any oxide on the surface. It didn't fall off, it dissolved. Because again, that oxide in contact with that metal is not stable. And so the oxygen went into the alloy, and now we can test that, because again, we're doing it all on tensile specimens. And now we have no ductility anymore, because now we get 5,800 parts per million oxygen in the alloy. And a relatively shiny specimen, once again. Not quite as shiny as it started, but we don't have the clear oxide formation on the surface. And you can see that publication that we had back in 2005. Now, last part about coatings. A lot of times you hear that coatings are going to solve all the problems. I'm going to go ahead and develop my alloy that has no oxidation resistance, and I'm going to coat it. And so two folks that I listened to for a long time, Ram Daroli and John Smegel, both had kind of negative feelings about coatings, but we do use them anyway. But they shouldn't be considered prime reliant. And so just a couple of quick comments that if you think about coatings for superalloys, interdiffusion is the biggest issue for coating lifetime. And again, we're the Department of Energy. We're looking at land-based gas turbines. We want long lifetimes. Again, used to be the bar was 25,000 hours. Now a lot of times they're talking about 40,000, even 50,000 hour lifetimes. The only way you're going to get that is to keep the coating temperature down relatively low. See a lot of testing in the literature at 1,000, 1,100, 1,150, 1,200 degrees C. But in fact, you can look at this specimen that's been exposed for 20,000 hours at 900 degrees C and see that we've already degraded sort of half the coating. The darker region is the beta, aluminum rich beta phase. And we've got depletion here. And because of interdiffusion, we've got depletion here. The alumina grit is marking that original interface between the coating and the superalloy substrate. So again, 900 degrees C doesn't sound very high, but that's about where a lot of land-based gas turbines are operating. Now that's the metal temperature. So you got a higher temperature because you've got a thermal barrier coating on top of that. And you might be able to improve it a little bit by other coating classes, but for these days, the industry is mainly using these M-Crowley type coatings. And again, I'll make the same point again. Interdiffusion is the biggest issue for coating lifetime. And here's a study on some steels. And again, we were trying to predict coating lifetime. For this particular study, for coal-fired boiler, 25,000 hour minimum lifetime is what we were told. You know, to get good sulfidation resistance, you've got to have more than 20 atomic percent aluminum in that coating. And that's very hard to do. Even if you start out with a coating that's 280 microns thick, it's quickly, due to interdiffusion, going to drop below that 20 atomic percent value at the surface in sort of 10,000 hours. And so you're down at 25,000 hours. Again, these are predictions made based on, we had some experimental inputs and then plugged them into the COSM model that NASA developed, Jim Nesbitt. And so you can see that, 700 degrees C is a tough goal. If you drop that down to 650 degrees C, then you got a sort of order of magnitude increase in your lifetimes, and maybe you're going to get a little bit longer life. But again, for steam environments or combustion environments, you need a lot lower aluminum content, kind of the shaded area here. And here's our prediction, and here's actually a coating failure. So we're not too far off with the model. But again, we're just modeling interdiffusion. You don't really even have to model the environmental effects. So finally, I'd have to say my summary here is not going to change much from previous talks. I think that defining the application will assist in defining relevant experiments, temperature, environment, stress, time. And for things like assessing ductility, subsides tensile specimens have been very useful. And I think, again, if you want to talk about embrittlement, then measure it. There's some challenging strategies out there. Developing materials without oxidation resistance and thinking that coatings are going to solve the problems is a challenge. And then finally, among thermally grown oxides, alumina is always going to have an advantage. I didn't get into this too much, but if you think about it, you still have to have a reservoir of aluminum in your coating or in your alloy in order to form that. And really, if you look at the numbers, some of the studies that NASA's done, when you start talking about 10,000 hour lifetimes, you're not going to go far beyond 1200 degrees C with any kind of coating. So you should just understand, none of the oxides are slow enough growing to really sustain long-term behavior at very high temperatures. So thank you.